In this video, let's try to answer miscellaneous true or false questions. So you write true T if the statement is true, otherwise write F. First off, exponential functions grow faster than polylogarithmic functions, which grow faster than polynomial functions. So in growth of functions, when we mention exponential, we're referring to 2 to the n, and polylogarithmic functions we are concerned with, say, n polylogarithmic, so n log of n. Let's go faster than polynomial functions. You have n squared or n cubed and so on. So which grows faster? Is it exponential? We could perform a quick check on the values for these functions. So we have, for example, 2 to the n. So if we plot say in the x-axis you have the number of operations, its complexity, and on the y-axis it will be the input n. And let's start, since this logarithm we cannot start with 0 is undefined, and 1 will just end up with 0. So let's just start with the value of 2, say 2, 3, 4, I think 8 will just do for our explanation. And if we start with 2 to the n, so let's have a logarithmic scale on the y-axis. So 2 to the n, you have, this is 2, for example, 2 squared, and 4. So let's just have 2, 4 powers of 2, say 8, and say 16, 32, say 64. So this is our number of operations y. So for 2 raised to n, we have, say, 2 raised to 1 is 2, so 2 squared will have 4, 2 cubed we have 8, 2 to the 4th will have 16, 2 to the 5th 32, and so on. So it will look like this basically. And when you reach 8, so at 8 the value will be delete this one. Anyway, at the value of 8, it will become, it's 2 to the 8 is 256, so it's 256 this point. how about the n log of n, or maybe n squared? So for n squared, you have, so it starts with 4 as well. So let's label this first to be 2 raised to n, the exponential. For the other one, so 2 squared will be 4, so this is for n squared. 3 squared will be 9, somewhere here maybe, 9, and 16, so they meet again here and intersect it again at 4. 4 squared 16, and 5 squared is 25, so it's now less than 32. 25, 6 squared 36, somewhere here, until it's 8 squared, it's just 64. So roughly we could represent it something similar to this. So this will be our n squared. And finally the n log of n, which is a bit tricky. So let's just focus on the powers of 2. So if this is 2 log of 2, log of 2 is 1, so 1 times 2 will be 2. So it will start at 2. Let's just pick what color, say purple. So when it is 2, you will get a 2 times 1, which is 2. When it is 4, you will get log of 4. Again, we are assuming base 2 here, as usually common in graph of functions. So we could also write this as n log n. Again, this is base 2. So for this, we could represent 4. So 4 times log of 2 squared, so times 2, 4 times 2, that will be 8. So here we have 8. So 2 squared is 2 times 4. And finally, for the power of 8, you have 8 times log of 2 cubed, which will give us 3. And 3 times 8 is 24. So less than 32, somewhere here. So this will be roughly our graph. And this is n log n base 2. So as we can see, the exponential grows the fastest, followed by polynomial, and the smallest will be the polylogarithmic, if we're going to compare the 3 functions. So that gives us exponential functions grow the fastest than polylogarithmic, but polylogarithmic grows faster than polynomial. So this is basically false. Because although exponential functions grow faster than polylogarithmic, it is polynomial that grows faster than polylogarithmic, as can be seen from previous graph. Second, a recurrence is a function defined in terms of one or more base cases and itself with smaller arguments. So this is true by definition for a recurrence. Caesar's encryption method can be represented by a function f that assigns to the non-negative integer p, which is the position less than or equals to 25. That is if we begin at 0, because there are 26 characters in the Roman alphabet, with fp equals p plus 3 modulo 25. Almost true. The only thing that is wrong is the modulo, because if you're going to come up with modulo 25, then the last letter is 0, the last letter z will be 0. So this is false, because this should be modulo 26. A pseudocode is a high-level description of an algorithm that uses the structural conventions of programming, which is intended for compiler. No. The pseudocode is not intended for the compiler, and especially it doesn't produce as executable application. So this is false. The pseudocode is intended for human reading, programmer communication, or just to express the algorithm in a precise way, in a precise manner, not intended for compilation, of course. Definiteness of an algorithm describes the property where it should be applicable for all problems of the desired form. Where it should be definite. This is not definiteness. This is generality. So this is false. So generality of an algorithm describes the property where it should be applicable for all problems of the desired form, not just a particular set of input. And basically that's it.